Welcome to Gradient Canvas. Today we're going to learn about cross-validation and data leakage, two ideas that decide whether you can trust a model's score. Your model scores 98% in your notebook. You ship it, and on real data, it falls apart. The evaluation didn't lie about the numbers. It lied about what the numbers meant. Two things decide whether a test score is honest: how you split your data and what secretly crosses that split. Those two ideas are cross-validation and data leakage, and together they're the difference between a score you can trust and a score that's fooling you. Start with the usual approach. Split your data once, say 80% to train, 20% to test. Here that split gives 91% accuracy, but watch what happens if we just reshuffle and split again. Now it's 84, again, 88. The score is swinging by several points, and nothing about the model changed. With a small test set, you're not measuring the model, you're measuring the luck of which rows landed in the test fold. We need an estimate that doesn't depend on one lucky slice. Here's the fix. Instead of one split, cut the data into k equal parts, call them folds. With 5 folds, you train on 4 and validate on the one you held out. Then you rotate. Each fold takes its turn as the validation set, exactly once. That gives you 5 scores instead of 1. Every single data point gets used for training and for validation, just never at the same time. Average the 5 scores, and you get a far more stable estimate of how the model does on data it hasn't seen. Formally, the cross-validation estimate is just the average of the per-fold scores, 1 over k, times the sum of the score on each fold. Say the 5 folds give 0.88, 0.91, 0.84, 0.90, and 0.87. The average is 0.88. And the spread from 84 to 91 tells you how sensitive the model is. Common choices are 5 or 10 folds. Push k all the way up to the number of data points and you get leave one out. Train on everything but one row, test on that row, repeat. Bigger k means more training data each round and less bias, but more compute. So 5 or 10 is the usual sweet spot. So cross-validation sounds bulletproof. But it rests on one assumption: the validation fold has to be genuinely unseen. Data leakage is any way information from outside the training fold sneaks into the model. When that happens, your cross-validation score looks great and still doesn't hold up on real new data, because the model was quietly graded on information it won't actually have at prediction time. Leakage doesn't crash anything, it just makes you confident and wrong. Here's the most common leak, and almost everyone does it at least once. You standardize your features, subtract the mean, divide by the standard deviation using the whole data set. Then you cross-validate. The problem: that mean and standard deviation were computed using the validation rows too. So the scaler already peaked at the data it's about to be tested on. The held-out fold isn't really held out. The fix is a rule. Every step that learns from data, scaling, imputing missing values, selecting features, must be fit on the training fold only, then merely applied to the validation fold. In practice, you wrap the preprocessing and the model together in a pipeline and cross-validate the whole pipeline so the fitting happens inside each fold automatically. Preprocessing isn't the only culprit. Target leakage is a feature that's really a stand-in for the answer, or that only exists after the moment you'd predict, like using was-prescribed antibiotics to predict has an infection. It's a fantastic predictor in training and useless in production because you don't have it yet. Temporal leakage is using the future to predict the past. If your data has time order, your folds have to respect it. And group leakage is when the same entity, say the same patient or user, appears in both training and validation. The model can memorize the individual instead of learning the pattern. Same fix every time. Make the split match how the model will actually be used. So, two ideas that work as a pair. Cross-validation rotates the held-out fold so every point gets a turn, giving you a stable, honest estimate instead of one lucky split. But that honesty depends entirely on no leakage. Fit every learning step inside the fold, and make sure your split mirrors how the model will really be used. The one line to remember: trust a score only if the data it was scored on was genuinely unseen. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please subscribe and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.